Hi, today I'm pleased to introduce our work on open-ended evolution in linear, an artificial life substrate recognized for its rich and continuous dynamics. It should be noted our method is agnostic to any simulation that can be rendered in 2D. We have developed a novel framework, ASAL++, inspired by previous work from Kumar et al. The central innovation in ASAL++ is leveraging foundation models to guide the search within linear towards configurations aligned with specified prompts. And once a suitable configuration is identified, a second foundation model proposes a new target prompt based on the video generated by this suitable configuration. This iterative process results in increasingly complex and lifelike behaviors, which one could think of as being analogous to some form of evolution. Illustrated here at the bottom is an example where we evolve from an initial configuration resembling an egg hatching to 7 generations. To contextualize, let's first revisit Conway's game of life. This environment operates on a discrete grid of binary states and simple yet Turing-complete rules, producing intriguing emergent patterns. Linear, developed by Chan in 2019, expands this concept by employing continuous state and smoother dynamics, generating richer and more diverse lifelike forms. Artificial life research, however, is not limited to cellular automata. For example, Reynolds-Boyd simulates collective animal movement in continuous space, and flow linear further enriches linear with fluid-like dynamics, allowing an even more sophisticated emergent phenomena. Building on these substrates and utilizing the modern methods of deep learning, Kumar et al. Introduces the ASAL framework, automating the search for artificial life. ASAL uses CLIP, a powerful foundation model that maps images and textual descriptions into a shared embedding space. Through CLIP, simulations can be systematically guided to match specific text prompts by optimizing the similarity between the visual simulations and target prompts. ASAL discovers diverse artificial life patterns using objectives such as a supervised target alignment, an open-ended novelty target, and illumination to explore simulation diversity. This work significantly inspired our own research direction. In the supervised target approach, ASAL optimizes simulations by maximizing the similarity between the final rendered state and the text prompt in CLIP's embedding space. Specifically, each simulation state is embedded along with the target prompt, and the cosine similarity is used to guide parameter adjustments iteratively. This optimization strategy yields distinctive configurations, exemplified here by some examples from the paper like a caterpillar or a pepperoni pizza in different substrates. Our motivation for pursuing open-ended methods can be explained in great detail by Stanley and Lehman's insights from their work Why Greatness Cannot Be Planned. Traditional goal-driven strategies can inadvertently limit discovery, missing out on valuable unexpected stepping stones. In contrast, open-ended exploration encourages adaptive and continuous evolution, much like natural selection, promoting richer diversity. Foundation models in this context act as surrogates for human observers, autonomously proposing and evaluating new evolutionary directions, thus enabling innovative discoveries beyond our explicit objectives. With all this in mind, we introduce ASAL++, incorporating 2 variations, the evolved temporal target. Both start with an initial prompt optimized by CLIP. Subsequently, Gemma 3, a multimodal foundation model, is prompted to suggest new evolutionary targets. This iterative cycle is repeated, continually evolving simulation configurations. In ETT, the entire chain of historical prompts is retained and optimized throughout, ensuring thematic consistency over time. In EST, only the most recent prompt is retained and optimized, allowing greater freedom to explore novel configurations at each iteration. The diagram illustrates this iterative approach, where geometry progressively generates prompts that guide the simulation. Our experimental evaluation, summarized here, compares the open-endedness of both variants using diverse initial prompts. Higher OE scores reflect greater continuous novelty. For the ETT method, the mean OE score was approximately 0.049, whereas EST achieved a slightly higher mean of 0.052. These results suggest that EST, by optimizing solely for the latest prompt, facilitates greater overall diversity across generations. Conversely, ETT provides more coherent evolutionary trajectories by integrating historical prompts, though with slightly reduced novelty. To conclude, I will now show you a live demonstration. This notebook implements both the EST and ESS methods, and in preparation for this, I have generated an EST sample using a caterpillar for 5 Gemma prompt evolutions, and will now display this. So you can see we begin with a caterpillar, which then develops into floating lichen, developing into floating colonies, further into symbiotic bioluminescent drifting structures, and into bioluminescent symbiotic fungal networks. This notebook also allows you to do this with the ETT method.